Hello and welcome. In this video, we're going to interpret the regression coefficient estimate results of a log level regression. So suppose that we have the following model that we wish to interpret the results of. So here we have log wage is our dependent variable, so our response variable. It's a function of an intercept here, so it's just a single number in the front, plus beta 1 times education, plus beta 2 times experience, plus beta 3 times age, and then our error term. So now suppose this model, let's say we've gathered a fair amount of data, we've ran the regression, and we get the following regression estimate results. First off, keep in mind that none of these are real. They're just completely made up by me. So don't take them at face value, but what we are going to focus on is how to interpret them if they were our results. First off, these are results that are pretty typical looking from an R regression output. So we have our intercept here standing in for beta 1. So this value here is our beta 1 value, so our beta naught value. The term next to education in our regression results is our stand-in for beta 1 here, so we get 0.33. Standing in for beta 2 is our experience regression coefficient estimate, so 0.12. And then next to age, we have 0.04 there. Now, how would we interpret something like this value for beta 1 of 0.33? Before we get into that, we have to get kind of across just a few assumptions that are required before we can make any interpretation of our regression coefficient estimates. So the first one is that Gauss-Markov assumptions hold. So there's several of these, and in fact we could still sometimes interpret our results if we relax these assumptions a little bit. But for the sake of this, let's assume that those Gauss-Markov assumptions hold. I think there's like 4 or 5 or 6 depending on how they're broken down. Next up, we need to assume that our coefficients are statistically significant and practically significant. So regarding statistically significant, how do we know that? Well, we look at our t-value and p-values here. So we have super low p-values for each of our regression coefficient estimates, so that we know that they're statistically significant. In terms of practical significance, that's a bit more qualitative. So for practical significance, is basically, does that regression coefficient estimate, is it big in a way that, again, it's qualitative. So I guess, is the effect size noticeably big? Maybe that's practical significance. Given the underlying variation in the variable you're concerned with, is the coefficient estimate large enough to have an effect that you might notice in the real world? And then lastly, we hold all the other variables constant when we're interpreting a single regression coefficient. So when we say interpret beta 1 here, we're assuming that experience and age are all also held constant. So giving those, holding those assumptions, let's interpret beta 1. So beta 1 definitely is going to tell us something about the effect of education on wages, but exactly how is it doing that? So to correctly interpret this, what we're going to do is we're going to take the differential of our model with respect to education. So that's what we're going to do here. So here's our basic model. Log wages equals beta naught plus beta 1 times education plus beta 2 times experience plus beta 3 times age. So taking the differential with respect to education, we get d wage over wage is equal to the change in education times beta 1. And then kind of rearranging stuff, we get the following. Actually, hold on, let's look at this. So d wage there is the change in wage, and the d education is the change in education. So d wage over wage is the change in wages in percent. So what's interesting about that is if you times this term by 100, so if you take that times 100, you'll get the percent change in wages. So if that thing that I've highlighted times 100 is the percent change in wages. So that's a useful statistic. So let's times both the sides here by 100. And we get the following. We get this 100 times d wage over wage, which again, this here is the percent change in wage, is equal to 100 times the change in education times beta naught. Okay, almost there, kind of reinterpreting this in hopefully language we can both understand a little bit more. We get the percent change in wages is equal to 100 times the change in wage, the 100 times the change in education times beta 1. So what is beta 1 here? What exactly does it mean? It means that if we increase education by 1 unit, we expect wages to increase by 100 times beta 1%. So with beta 1 equal to 0.33 here, that means that if education were increased by 1 unit, so that's 1 year, education increases by units of years, we expect wages to increase by 33%. So to correctly interpret this, we need to be aware of a couple things. So first off, we need to be aware of what the units are of changes in education. And then we also need to know, obviously, what beta 1 is. So what this says, again, is that a one year increase in education, we expect to increase wages by 33%. We could also interpret experience here. So once again, assuming these kind of big assumptions here hold, we expect a 1 year increase in experience, since experience is here recorded in units of years. 1 year increase in experience, we expect to increase wages by 12%. And then age, this data happens to record age in years. So a 1 year increase in one's age, we expect to increase wages by 4%. Great, hopefully that's helpful. If it was helpful, if you wouldn't mind giving me a thumbs up, and thanks and have a good day. Bye.